Good morning, good afternoon. Welcome to today's Lubrizol360 webinar. My name is Charu Tripathi, and I will be the moderator for today's discussion. Before I introduce our presenters, I would like to take a few moments to go through some housekeeping items. Your microphone are all muted automatically. Any questions, you can submit them using the Q&A feature in WebEx. This should be in the right-hand side panel of your screen. You will only see your questions, and I will use these in the Q&A session after the presentation. I may combine similar questions together, and we may not get to all questions. Today's presentation is scheduled to last for 30 to 40 minutes, and the recording and a copy of the presentation will be made available afterwards. I would now like to draw your attention to the following antitrust statement. Today's webinar is being presented by Lubrizol for the purpose of providing information and insight into the markets and applications into which our products are used. This may include how performance and/or end-use requirements for those products are changing, and how our products perform against existing or future requirements, which have yet to be finalized into performance specifications. As certain attendees participating in this webinar may be competitors of each other, we will be conducting this webinar in strict compliance with the antitrust and competition laws. For this reason, competitively sensitive subjects, some of those are shown on the screen, may not be discussed at any time, and any questions that are submitted to the area shown will not be asked. At Lubrizol, safety is the top priority of our organization, and we start every meeting by sharing a safety moment. This provides the opportunity to discuss and reflect on topics that can help ensure we all remain safe at work and at home. Around the world, kids are going back to school, and that means back to driving basics. Here are a few tips to ensure everyone stays safe. Obey all traffic signals and speed zones when driving near schools. Watch for students on bicycles and walking, especially at intersections and driveways. Obey all crossing guard instructions where applicable. Kids love their phones and are often not paying attention. Don't assume everyone sees you. Back to school often means new drivers on the road. Limit your own personal distraction. Allow yourself extra time in the morning to anticipate more traffic on the road. Reduce speed limits in areas and frequently stopping buses. I would now like to introduce our speakers for today, Drs. Growney and Robin. Dave Growney is a research chemist with strategic research. He practices colloid science, and the focus of his current research is in and around engine lubricant degradation. Prior to working for Lubrizol, he earned both his PhD and Master's in Chemistry from the University of Sheffield. The focus of his PhD was the investigation of diesel soot dispersion in engine lubricant. Matt Robin is a technology manager with strategic technology. He is responsible for Lubrizol's strategic technology portfolio covering engine oil acidification and corrosion control. Prior to joining Lubrizol in 2016, Matt worked in academia as a research fellow for 2 years. He has a PhD in chemistry from the University of Warwick, a master's in chemistry from the University of Kent, and a Bachelor of Arts in Natural Sciences from the University of Cambridge. Today, Dave and Matt will be discussing whether TBN and TAN data provide the full story of how lubricants age inside engines. I will now turn it over to Matt. Thank you.
Good morning and good afternoon, everyone, and thank you for joining us today. The question we will be discussing in this webinar is, how do we best measure lubricant aging inside an engine in order to protect our end users and keep their vehicles and businesses running smoothly? My name is Matt Robin, and I'll be presenting today with my colleague Dave Growney. Before getting to the outline for today's talk, I just first want to frame that question: how do we best measure lubricant aging inside the engine? Let's start by considering the way lubricant aging is currently measured for light-duty and heavy-duty vehicles. So we use chemical analysis to determine the extent to which the oil is broken down and the extent to which contaminants have accumulated in the oil. So, for example, we measure the buildup of wear metals, soot and fuel dilution, and we also measure the viscosity changes and the oxidation and nitration which result from oil degradation. Acidification is also very important, and that's measured with two titration methods being used to calculate the total acid number, the TAN or TAN, and the total base number, TBN. Our specific focus today is monitoring that acidification of the lubricant. So how does acidification occur? Well, it's really via two routes. Firstly, acids form during fuel combustion and can accumulate in the lubricant. And secondly, acids also form via the thermal and oxidative degradation of the lubricant, which is due to the harsh operating conditions inside the engine. The drive for improved efficiency and reduced emissions has had an impact on lubricant acidification. For example, the adoption of low sulfur fuels to reduce sulfur dioxide emissions, the introduction of after-treatment devices, such as particulate filters, EGR and SCR, and also the drive to extend oil drain intervals. So this means that protecting vehicles against the negative effects of lubricant acidification, such as corrosive wear, have never been more important. And the importance of this issue therefore raises that question: are the current methods being used for measuring acidification providing the right information to protect engine hardware and keep vehicles on the road? So there are three key elements to answering that question of how do we best measure lubricant aging. We must consider used oil analysis methods, changing fuel and hardware, and corrosion protection. Throughout the history of lubricant development, two titrations have been used to understand that buildup of harmful acid which occurs during operation. And these are the total base number and total acid number titrations. However, technology doesn't stand still, and our research at Lubrizol has led us to conclude that these TBN and TAN methods are no longer sufficient for monitoring lubricant condition. This research has also led us to conclude that measuring IPH for used oil analysis is the best way to ensure the integrity of your vehicle's lubricant. So by using this standardized test method for automotive lubricants, we believe it will be possible to maximize the lifetime and efficiency of your engine. So we'll share a summary of that research today, and it will be organized in the following agenda. In the first section, I'll discuss the buildup of acids in a lubricant and the current methods for measuring this. Then in the second section, Dave will explore how detergent chemistry and the protection detergents provide is far more complicated than simply the amount of TBN in a lubricant. In the third section, I will look at some of the challenges and shortfalls of using TBN retention to describe lubricant degradation. And then in the fourth section, Dave will close with the opportunities and advantages provided by adopting the ASTM Z356 IPH method to measure acidification. So let's start with a bit more detail on the way in which acids build up in a lubricant and the traditional TAN and TBN methods which are currently used to measure acidification. So I just said that fuel and hardware have an impact on lubricant acidification. So let's take a closer look at why this is. We can classify the acids that build up in a lubricant into three separate chemical classes: sulfur acids, nitrogen acids, and organic acids. Sulfur acids, depicted in green, derive from combustion of sulfur-containing species in the fuel. Nitrogen acids, depicted in purple, derive from the formation of NOx during lean combustion. And organic acids, depicted in blue, derive from incomplete combustion of fuel hydrocarbons and from oil oxidation. Therefore, as fuel quality changes, the composition of this mixture of acids will also change. For example, in Europe, as sulfur levels in fuel were sharply reduced in line with Euro 2 to Euro 5 legislation, the relative significance of sulfur acid contaminants decreased. Emissions legislations to limit NOx and increased fuel economy have also reduced the significance of nitrogen acids. So therefore, the relative importance of organic acids have increased over time. At this point, it's also worth mentioning why acidification is so significant and why we're so interested in making sure we can measure that properly. And the reason why we worry about acids building up in the lubricant during an oil drain interval is because ferrous metals, such as cast iron or steel, are both corroded by acids. Then the abrasion of that corrosion, where it's present on running surfaces, will lead to corrosive wear of engine components, and that will ultimately lead to loss of performance, which can impact efficiency and also lead to increased emissions. Therefore, it's crucial to protect against acidification and the associated corrosive wear with a high-performing engine lubricant. And as we will discuss in more detail in this webinar, lubricants are formulated to contain basic additives and corrosion inhibitors, which will control acidification and prevent corrosion. Currently, the industry relies on total acid number and total base number titrations to understand the acidification of engine oils. And there are many different titrations used for oil analysis. So on this slide, I've picked out 3 very common examples. For measuring TBN, we have the ASTM D2896 and D4739 measurements. And for TAN, we have ASTM D664 measurement. Each measurement uses a titration solution. In this case, the TBN method uses an acid titrant, and the TAN method uses a base titrant. The titration method also requires a solvent for the sample being analysed, and it's these different combinations of titration solution and solvent system which lead to the different features of each measurement. So for example, that will affect the precision or the extent to which different types of acid or base will be measured. To be able to interpret TAN and TBN data measured by titration, we really need to understand that titration process. So let's take a look at an animation of the ASTM D664 total acid number titration. Pictured here is a used oil sample containing acid, and the acid is denoted as H+. And that's because the positively charged hydrogen ions are the reactive chemical species within the acid. The sample is first prepared by adding the solvent, which in the case of the D664 measurement is a mixture of isopropanol, toluene and water. At the beginning of the titration, a pH meter is added to the sample, and that's measuring the H+ concentration. Then during the titration, potassium hydroxide, which is denoted here by its chemical formula KOH, is added to the sample as we measure the pH. At the beginning of the titration, the pH will be low because the sample contains acid, and the amount of acid is going to be determined by measuring the change in pH during the titration. As the hydroxide is added, it reacts with the acid in the sample in a neutralization reaction, and this acts to increase the pH as the sample becomes less acidic. As the last of the acid in the sample reacts with potassium hydroxide, the change in the pH is steep as it moves past neutral. And then as more and more potassium hydroxide is added, it will now accumulate in the sample, making it basic and leading to a high pH. Eventually, the pH will then plateau at a high pH at the end of the potassium hydroxide addition, and this produces our classical titration curve. The total acid number is then calculated from the inflection point of that curve and is equivalent to the volume of potassium hydroxide that had to be added to neutralize all the acid in the sample. When the sample contains strong acids, such as shown in blue here, that inflection point will be sharp and well defined so that the TAN can be calculated from the inflection. However, if the sample contains a mixture of weak acids, the inflection point will be poorly defined, as shown here in orange, so that the TAN is then calculated from the buffer endpoint. What that means is a pH 11 buffer is used to calibrate the pH probe, and then by comparison at the point at which the sample reaches pH 11, That's taken as the point at which all the acid in the sample has reacted. So I'm now going to pass over to Dave, who will cover the second section.
Great, thanks, Matt. So in this next section, I'm going to tell you a little bit more about what we add to our lubricants to protect against acidification and why it's more complicated than TBN. So first of all, what do we add to our lubricants? So over-base detergents are the primary additive that are designed to neutralize the harmful acids that Matt has been telling you about. So on the top right of this slide, I've got a schematic cartoon of what these look like. So you've got a metal carbonate particle, and it's stabilized by what we call surfactant, which is depicted by those purple structures. And these keep it soluble in the oil, so they keep it stable. So the diameter of those particles is between 4 to 10 nanometers typically, so they're very small particles. And that structure we call an inverse micelle. So more specifically, the metal carbonate can be the calcium or magnesium carbonate. Those are the typical metals used in these additives. And we can have different surfactants used as well. So those purple structures can be different in chemical nature, and you can see on the bottom of this slide 3 examples of those. So we've got sulfonates, salicylates, and phenates. So they're the 3 most common surfactants used. I'll also make it clear at this point that the cartoon on the right is a perfect sphere. However, sometimes these particles can be different shapes and sizes, so that needs to be remembered when we think of these structures. So finally, I just wanted to point out that we've done a lot of work internally on these additives to understand them intricately as described. So on the bottom right of this slide now is a neutron scattering data set. So here we've used neutrons to understand shape and size and morphology of these particles. So with all that in mind, let's move on to the next slide, where I'm going to tell you a little bit more about some of the intricacies of these additives and how that translates all the way through to a finished engine oil formulation. So on the top of this slide, I've got 3 different over-base detergents. All of them are magnesium sulfonate, so they have a magnesium carbonate core and then the sulfonate surfactant shell. But they have a key difference, and that is the TBN that they were synthesized to. So on the far left at the top, we have a 400 TBN magnesium sulfonate, and then we have a 300 in the middle and a 100 on the right. So the only difference between these 3 over-base detergents is the total base number that they were synthesized to. And then you might have noticed that to the right of each of those boxes, I have some purple spheres. And as you can see on the top right of this slide in the key, this is just a simplification of that structure I showed you on the previous slide. So when the TBN is different in these additive materials, the size of those particles is also different. So on the far left at 400 TBN, we have bigger particles, and then on the right, we have much smaller particles. So you can think of the TBN and the size of the particles as related to each other. Okay, so now let's try and make a 5 TBN finished lubricant with each of those different additives. So let's move down to the bottom half of the slide now. So on the bottom left, to get 5 TBN from that 400 TBN over-base detergent, we need 1.25% of that to get to 5 TBN. And then as we go across, at 300 TBN, we'll need a bit more because there was less space to start with, so we need 1.67 to get to 5 TBN. And then finally on the right, we started at 100 TBN, so we need 5% of that additive to get to 5 TBN. So essentially, as we moved across, we need more and more of that stock additive because the TBN was lower as you go across. So what does that mean when we think about the particle shape, size, and number? So they're all spherical, so we don't have to worry about the shape here. If we think about the size on the far left, we have larger particles in that 5 TBN finished lubricant. And because we didn't have to dilute, because we didn't need as much of that additive, we actually have a smaller number of larger particles in that bottom left scenario. Whereas on the other extreme, on the bottom right, we needed more of the additive and the particles are smaller. So we have a larger number of smaller particles on the bottom right. So essentially, when those finished lubricants are all the same TBN, however, the number of particles and the size of particles is going to be different between those. So then you might think, well, okay, fair enough, but why does that matter? Well, the reason that matters is because different particle sizes have different surface area to volume ratios. So on this slide, on the y-axis, we have percent acetic acid remaining. So what that means is we've neutralized acetic acid, which is one of the harmful organic acids Matt's told you about already. We've neutralized acetic acid with our over-based detergents, and the lower the number, the better, because we've neutralized more as we go down that axis. And on the x-axis, we have surface area to volume ratio. So a big particle will have a low surface area to volume ratio. So there's a lot of volume hidden inside versus how much surface there is. And then a small particle will have a high surface area to volume ratio. So we have a lot of surface area per volume. So you can see on this graph, there's a distinct trend between these three additives, where the low surface area to volume ratio neutralizes the least, and the high surface area to volume ratio neutralizes the most. So this is now demonstrating that the size of those particles that end up in your 5-TBN lubricant is actually going to influence how good they neutralize that acid. And importantly, the TBN will not pick this up because remember, they were all 5-TBN. So it's more intricate than just thinking about the TBN there. Okay, moving on to the surfactant. So I told you a couple of slides ago that there's different surfactants you can use to stabilize these particles. So we have sulfonates, salicylates, and phenates typically. Again, our y-axis is acetic acid remaining after neutralization, where the lower the number, the better. We've neutralized more. And you can see here that there are differences between the three different surfactant types. So here we've got calcium carbonate surrounded by different surfactants. Noteworthy that there's the same surface area to volume ratio in this comparison. So we don't have to worry about everything I just told you about regarding size of the particles. So at the same surface area to volume ratio, we get differences in neutralization potential. And this is driven by the surfactant itself. So this isn't necessarily due to the particle size or the metal type. And again, this will not be picked up by a TBN titration. So all of these are the same TBN in this experiment, but you can see they're neutralized to different extents. And then finally, in this part, I wanted to compare both metal type and TBN. So I'll talk you through this step by step. Again, on our y-axis, we have acetic acid remaining, so the lower the number, the better. On the left-hand side of this graph, we have a comparison of two different 400 TBN over-based detergents. One of them is a magnesium sulfonate, and one of them is a calcium sulfonate. And then on the right, we have, again, the same comparison, magnesium sulfonate versus calcium sulfonate. However, the TBN is lower at 185 respectively. So let's start on the left-hand side. Let's compare the orange to the yellow. So they're both the same TBN, so we don't have to worry about particle size. They both have the same surfactant, so we don't have to worry about the surfactant making any changes to the performance. So therefore, it must be the metal that is giving us this trend. So the magnesium is less effective than the calcium at neutralizing acid in this instance. But this makes sense to us scientifically because calcium carbonate is more basic than magnesium carbonate. So it's a stronger base, it will neutralize more acid. If we then look on the right-hand side of this plot, we've got the same comparison. First of all, if we look at the blue versus the green, again, the calcium is neutralizing more acid than the magnesium. We expect that. And then let's compare the left-hand side of the graph to the right-hand side of the graph. So now you can see that on the right, generally the numbers are lower. So we've got a higher performance there. And that's because the TBN is lower. So we have smaller particles, higher surface area to volume ratio, better neutralization. But then finally, I just want to compare yellow to blue because we have a 400 TBN calcium sulfonate and a 100 TBN magnesium sulfonate, and they both give essentially equivalent performance. And this is a really good demonstration of the fact that although I've been telling you different levels of performance depending on different variables, in reality, you can get to the same performance with lots of different over-base detergent types. You just need to optimize with all of these concepts in mind. Finally, I'll just point out we've recently published a paper on all this information where we discuss it in a lot more detail, and there's a reference below the graph for that paper in SAE Fuels and Lubricants. Okay, so for the final part of this section, I just wanted to move on to a slightly different scenario for acid neutralization. So everything we've talked about so far has been in non-aqueous fluid. So it's essentially acid in the oil being neutralized by over-base detergents in the oil. However, we also have to think about water. And the reason for that is because water is a product of the combustion of fuel. And if the temperatures in the engine are low enough, we'll get some condensation forming, and that condensation, that water, can actually pass between the air and the oil over the air-oil interface and be stabilized as a water droplet in the oil, as you can see on the top of this cartoon. So we have a lot of free surfactant in our engine oil. So that surfactant will essentially encapsulate that water and will form a water droplet. And then importantly, the short chain organic acids that can be corrosive in your engine are also very water soluble. So we can get to a scenario where we have acidic water droplets. And these water droplets, we need to be able to target and neutralize that acid with our over-base detergents. And that's exactly what happens. So you can see on the bottom right of this cartoon, we have a calcium carbonate over-base detergent, and it's collided with one of these acidic water droplets. The calcium carbonate will partition into the water, and then we'll get neutralization, from which we will get a salt, which is then stabilized in one of these droplets. So we then have these droplets of neutralized acid that are therefore not harmful anymore. So with that in mind, let's look at performance. So on this slide, on the left-hand side, we now have aqueous acid neutralization. So a bit different to what we were talking about before. We typically use a rate for this sort of neutralization experiment. So now the y-axis is a little bit different. So we have a rate value where the higher the number, the better, because it was a faster neutralization. And we've got a 400 TBN magnesium sulfonate compared to a 400 TBN calcium sulfonate. So the only difference here is the metal type. Everything else is kept constant. And you can see a very different performance there, where the magnesium sulfonate appears to be a lot more, a lot higher in performance than the calcium sulfonate. So if we move to the right-hand side of the slide, what I've done is I've brought some data I've already shown you back onto this slide to compare directly to the left-hand side. So we've already looked at these two over-base detergents in the non-aqueous environment a few slides ago. Important to note, I've now flipped the y-axis. So now the higher the number, the better. We're looking at acetic acid neutralized now rather than remaining. And I did that so you can compare very simply and directly to the left-hand side. So now you can see that in the non-aqueous environment, the trend is the opposite. You might remember I told you calcium carbonate is more basic than magnesium carbonate, so the neutralization will be stronger. Okay, so what does that mean on the left-hand side of the slide then? So why have we changed the performance there? And the answer is magnesium carbonate is more water soluble than calcium carbonate. So in an aqueous environment, it's the magnesium over-base detergents that can often dominate the neutralization, because essentially they can get into the water more easily. They're more water soluble. So again, something you have to consider depending how low the engine operating temperatures may get. And again, something that the total base number just won't pick up. All of these are the same total base number. Okay, so with that, I'm going to pass back to Matt for the next section.
Thanks, Dave. So as Dave just explained, the function of base within the lubricant is complex, and acidification is influenced by more than just the TBN of the formulation. And for this reason, we must take care when we interpret TBN measurements of lubricants. A commonly used metric for measuring the aging of a lubricant is TBN retention. So that's the measurement of TBN at the end of an oil drain interval. And the typical interpretation is that TBN retention is a desirable characteristic. So I want to examine that idea a little bit more closely. This illustration depicts a lubricant which contains base, and the base is displayed here as TBN. Then during use, acid, which is depicted here as H+, will form and accumulate in the lubricant. If that base is ineffective and doesn't react with the acid, then the TBN will be retained, and it will be measured in the used oil. However, the acid concentration is high. Alternatively, on the right-hand side, we have a similar scenario, this time with effective base. And because the base is effective, it reacts with the acid, and these neutralization reactions remove both the acid and the base from the lubricant. So by the end of this oil drain interval, only a small amount of base is remaining as a reserve, whereas most of the base has performed its intended purpose and reacted. So in this case, the TBN is depleted because it is functioning as intended, and it's keeping the acid concentration low. And because we're concerned about acidification and the potential for acidic corrosion, it would actually be more useful to measure the amount of free acid rather than trying to understand it through looking at TBN depletion. So in analogy, to illustrate this issue, if you bought some popcorn at the beginning of a movie, and then by the end of the movie, like on the left-hand side, the popcorn retention was high, we would understand that as the popcorn being ineffective. So it's not very tasty, it's not very good, it's not doing its job, and so there's still lots left. However, if at the end of the movie we have a situation on the right-hand side, I think that's the one we're all familiar with, where we have an almost empty box, we would understand that the popcorn depletion was a good thing. So it's doing its job, it's really good, and we're really enjoying it. There's a second example we've got here of, again, the difficulty of interpreting TBN depletion. And it can be demonstrated in the following experiment, where we look at neutralization of different types of acid by an engine oil detergent. In this experiment, we blended over-base detergent into base oil to a final TBN of 4, and we blended acid into a base oil to a final TAN of 3. We then mix those samples together, and we're going to measure TBN retention via titration. In this experiment, we would expect TBN to deplete to 1, as TBN and TAN cancel each other out via the neutralization reaction. So we expect the titrations to show that TBN depletes if neutralization occurs, or we expect TBN to be retained if the acid isn't neutralized. And TAN will only be measured if there is unneutralized acid remaining. So let's take a look at the data for 2 different types of acid. And firstly, we did this experiment with sulfuric acid, which is a strong sulfur acid. The reaction proceeds according to our expectations here, with TBN and TAN being consumed. And as a result, we measure TBN for the sulfuric acid addition to be about 1, with a TAN close to 0. The strong sulfur acid is consumed by the strong calcium carbonate base of the detergent, and the products of the reaction are not titrated. So therefore, the system is behaving according to our expectations. So in the second example, we're going to use acetic acid, which is a weaker organic acid. Again, we have 4 TBN of detergent and 3 TAN of acid. And when we mix them together, the neutralization reaction occurs again, and we will have 1 TBN of excess base remaining. But the products of this reaction are also basic. The calcium acetate byproduct of neutralization is a weak base, and so it's measured by the TBN titration. And we see this in the titration data, which shows that for the acetic acid addition, TBN is still about 4. But we know that the acid has reacted because the TAN is close to 0, However, it's because these byproducts are basic, we cannot differentiate them from the original detergent base in the using the TBN titration. So in this case, it's defying our expectations that we would be measuring useful detergent base in that TBN titration. So we understand why 4-TBN is being measured, but it does not follow the expectations of using TBN titrations to be able to follow the course of acid neutralization. So again, we're seeing the difficulty in trying to understand engine oil acidification by using TBN measurements. And really, the root of the problem is we're interested in acid concentration because we're worried about corrosion caused by high concentrations of strong acid. But we're measuring base content, so we're kind of looking in the wrong place. And the complexity that using TBN and TAN titrations and their interpretation means that care must be taken when viewing real-world used oil data. This graph here shows iron wear and the TBN and TAN measurements from drain oils taken during a field trial conducted on high sulfur fuel, which will lead to high levels of sulfur acid formation. The x-axis here is TBN minus TAN, so the crossover occurs at 0 where I've placed that vertical dashed line. The y-axis is iron wear. It's measured by ICP, and the horizontal dashed line here indicates a critical level of iron wear. In this case, the TBN TAN crossover is a good indicator of the point at which iron wear is reaching a critical level. And this is because the TBN and TAN titrations were designed around strong sulfur acid contaminants, which we saw in the experiment just now behave according to our expectations. So in the past, when high sulfur fuel was more prevalent, or in locations where high sulfur fuel is still prevalent today, the TBN TAN crossover can be a useful indicator. In contrast, the data on the right was collected from a field trial conducted using low sulfur fuel. So in this case, TBN TAN crossover is not a good indicator of that critical level of corrosive iron wear. And that's because it's weaker organic acids that are more significant when using low sulfur fuel. We see at that TBN TAN crossover, the iron wear is actually minimal, and therefore it would be a mistake to condemn this oil based on that TBN TAN crossover, because the oil is still protecting these vehicles against corrosive wear. I'll now hand back over to Dave for the final section of this presentation.
Brilliant, thank you, Matt. So in the last section of this presentation, I'm just going to be telling you a little bit more about the IPH test method, which has been mentioned in the first few sections. So to start with, what I've done here is I've pulled up a table that Matt has already presented to you. It's just a slightly simplified version now. And it lists the 3 different test methods that you might be familiar with regarding oil degradation. So we've got the fresh and used oil TBN on the left and middle, and then we have the used oil TAN, the ASTM D664 over towards the right. So on the far right of the table, I've added on the used oil IPH, which is ASTM D7946. And we can now compare it to the other 3 test methods. So first of all, you'll see that there's no titration solution. And the reason for this is it's not actually a titration test method, unlike the other 3, and we'll go into that in more details in a minute. However, the solvent system is exactly the same as the solvent system for the ASTM D664 or the TAN test method. So that's something that, again, I'll explain in a minute. That's quite an important thing to use as an analogy. So if we finally look at the features, we can look at strong and weak acids if we look at the ASTM D664. However, the ASTM D7946, the IPH test method, only measures the acid strength. So what do I mean by that? So let's go back to one of these plots that Matt has already explained to you. So this is a titration curve, and this is how the ASTM D664 TAN titration works. So you can see here in blue we have some strong acid being titrated. So we've got quite a steep curve. And as Matt told you earlier, the inflection point is the place at which you read your volume of potassium hydroxide. If we have a weaker acid, then we have a more gentle curve, and it's the buffer endpoint at pH 11 which defines where you look at on your x-axis to define how much potassium hydroxide was neutralized. So two very different scenarios here. We've got a low and a high tan as a result of that. So how does IPH relate to this sort of plot? So it's worth noting, I said a minute ago, I'm going to say it again, it's not actually a titration, but it's related to this titration because it's the point at which this titration will start. So I've highlighted in green on the y-axis there, the start point of these two curves. So we've got a pH of 2 and a pH of 5. This is essentially what the IPH test method does. It looks at the start point of what would be a titration if we took it that far. Okay, so now let's think about what each of these data sets means, or how will it read in each test method. So if we start with the blue data, we have a low IPH, so we've got an IPH of 2, and a low IPH means a strong acid. We also have a low tan because the intercept of the x-axis is quite a long way to the left. So low IPH and a low tan. And then conversely, let's look at the orange data. Now we have a higher IPH of 5. So that means it's a weaker acid or less acidic. But we also have a high tan, so a lot of acid is there. So what I want to do now is just bring this, I suppose, a little bit closer to home and use an analogy that's a little bit easier to understand. So if we think about the left-hand side, so the blue data, we have a small amount of strong acid. On the right-hand side, we have a larger amount of weaker acid. And you'll see I've animated some pictures up there. I think as an audience, we can probably understand which of those is going to be more harmful to us. On the left, we've got some strong hydrochloric acid. That's something you definitely wouldn't want to get anywhere near your skin or your eyes. Whereas on the right-hand side, we've got a large amount of a weaker acid, which is lemon juice in this case. And we all know that that's something you can actually use on salads. You can cook with it. That's not going to be harmful to us at all. So is it better to have a small amount of strong acid or a large amount of weak acid? I think we both know which of those two we want in our kitchen. So in reality, it's the left-hand side that's going to be more harmful. So therefore the blue data. And importantly, that's the one that has a lower tan, which is the way we used to say the oil wasn't quite as degraded as it could be. So the IPH picks up the acid strength rather than just how much acid is there. That's the key thing to take home here. So let's relate that to some field trial data. So here we did 7 different field trials with over 50 different vehicles, and each point on this graph is from a different drain oil. So we've got over 600 drain oil samples on this graph, and this was from a heavy-duty diesel field trial. Similar to what Matt showed earlier, we've got the ICP iron content in parts per million on the y-axis, and then now we've got this IPH value on the x-axis. And you can see as we go to the left-hand side of the x-axis, as we reduce the IPH, we're increasing the strength of the acid, and we're seeing more iron. So you can see there's essentially a trend as we go to the left. However, we thought more about this data, and actually a pH scale is a log scale in its own right. So what we wanted to do is make the y-axis a log scale as well. So then we have a log-log plot to compare the data. And as you can see here, when we put a log scale on our y-axis, we get a very strong linear correlation with all of that data, where the lower the IPH, the stronger the acid and the higher the iron content in the drain oil. And this makes sense to us if we think about what Matt told you earlier about the corrosive wear mechanism. So the strong acids lead to corrosion, which can lead to more iron in your engine from the wear of that corrosion off the surface. And then finally, we also wanted to then do the same comparison with total acid number that we're more familiar with in the industry, D664, and that's what's now on the right-hand side of this slide. I've also added the R² values for the middle and the right-hand plot to define how strong that correlation is. And you can see in the middle, the R² is 0.7, so that's a pretty strong correlation, whereas on the right it's 0.32, which is close to no correlation. It's not really showing us a trend. And you can see that visually as well with that data. It's essentially a scatter plot without a given trend. So now this is showing you that the total acid number was not picking up that iron increase, which is actually linked to acid strength, but the total acid number was looking at all acid content, whether it's strong or weak, and that's not as useful to us. So to finish off, I was just going to cover some imagery, just to kind of hammer the point home in terms of how acid strength links to corrosion. So on this slide, I've got some pictures of some crankshaft pieces. So these are pieces of crankshaft out of an engine. And what we did is we submersed each of these separately into a container, a sealed container. We submersed the test piece in either an acidic solution or just a solvent with no acid, which was the control experiment on the far right. As you can see, as we work from the middle to the left of this slide, we're getting stronger and stronger in terms of our acid strength. And that is trending with the IPH as well. So below the images, I've put the IPH there, and you can see the IPH is going lower and lower, which means stronger and stronger acids. Now, it's important to note that all of these solutions were the same TAN. They were the same total acid number. It was only the strength of the acid that was different. And it's very clear that as you go to the left, the corrosion is getting worse and worse. So three acidic solutions that were exactly the same TAN gave you different corrosion amount, and it was all linked to the strength, which we managed to pick up with the IPH. Okay, so just to finish off, I'm going to summarize what you've heard today. So first of all, Matt's given you some of the background on the TAN and TBN measurements and how they're used to measure acid and base in engine lubricants, and how the industry's changed away from sulfur acids towards organic acids primarily. I've then told you a little bit more about the additives we use in the oil to neutralize the harmful acids, and the over-base detergents have different kind of structure performance relationships that mean it's more complicated than just saying it's a TAN and therefore it will protect. Sorry, a TBN and then it will protect. So moving on from that, Matt told you a little bit more about the titration methods and how they work, and why with these organic acids, often looking at TAN TBN crossover, for example, doesn't work for us because often the neutralized acid will measure as TBN as well. And then finally, I've told you a little bit more about the IPH test method and how it's a really strong way of indicating the corrosivity of our oil, because it links to the acid strength rather than just how much acid is there. So essentially, the inclusion of IPH in used oil analysis ensures the integrity of vehicle engine lubricants. And with that, I'm going to hand back over to Chiru to field the Q&A.
Thank you, Dave. And thank you, both of you, for sharing insights on measuring lubricant lifetime. A lot of really great questions have come up during your presentation, and we'll do our best to address as many of those as we can now. Starting with you, Matt. So someone has asked, what is the difference between TAN test and ASTM D664? I think they're trying to ask, what is the difference between TAN D664 and IPH?
Okay, so the D664 TAN test is a titration. So you're adding base to the sample, and you're using that to try and work out the total amount of acid. And because you add a strong base, you actually detect all of the acid in the sample. So like Dave was saying, you measure strong acid and weak acid, and you just get a number depicting the total amount of acid in the sample. Whereas the IPH, that's kind of a single point measurement. You just look at the pH of your your sample. And so that gives you an indication of the acid strength. So pH measures the H+ concentration, so you're getting a measurement of acid strength. And so that's the difference in how the methods work. And the difference in the data interpretation is essentially that point that Dave ended on, which is the acid strength is the part that is directly related to corrosion, because the stronger an acid, the more reactive it is with the surface. Whereas TAN is just telling you the total amount of acids, but those acids could be strong, or they could be weak, or they could be a mixture. So it's really a lot harder to relate that measurement to the thing we're really interested in, which is how much of a corrosion risk there is for the engine hardware.
Okay, yeah. Thank you. Next question is for you, Dave. Can you go into a bit more detail as to why over-base detergent surfactant matters when it comes to acid neutralization performance?
Yeah, sure. So I told you earlier that there's typically 3 different surfactants. We have sulfonates, salicylates, and phenates. And I showed you that the performance was different between those 3. So it's all to do with how strongly bound those surfactants are on the metal carbonate particle. I showed you that for the sulfonates, the performance was the weakest out of the 3. And that's because the alkyl sulfonic acid, basically the head of the surfactant, is going to be really strongly bound onto those particles. So you'll get a very, I suppose, impenetrable layer of surfactant on those particles, which means when acid comes along, it's harder for that acid to get in to the metal carbonate particle and neutralize. It's not to say it won't happen. You saw that there was still neutralization. However, it will be a little bit harder versus the likes of the salicylates and especially the phenates, where the surfactant is a lot more weakly bound onto the particle. So therefore, it's very easy for it to be liberated. It moves away and the acid can neutralize on the surface. And then on top of that, if we move to the salicylates and mainly the phenates, often the surfactant itself can neutralize acid when it's an organic acid like acetic. So you can actually have a surfactant acid neutralization because the surfactants themselves are slightly basic. So it all gets quite complicated mechanistically. But the important thing to note is that the TBN would be the same for all of those, because this is intricate kind of mechanistic differences rather than how much base was there essentially.
Yeah. Thank you. And next question is also for you, Dave. So since with the lower sulfur fuel, TAN and TBN crossover does not indicate discard life, and TAN rise will be lower, does it call for a review on the FE ppm discard limit?
Yeah, good question. So I think so. Matt's already shown you. Matt showed you some field trial data where he had the TAN TBN crossover, and the fact that if the fuel has less sulfur in it, we just don't reach that critical ion limit at that crossover point. I think looking at iron content is a good way of understanding how degraded your lubricant is, or I suppose how much wear you're getting in your engine, which can be linked to the oil degradation. However, focusing on TAN TBN crossover as the primary measure to understand the lubricant degradation is something that you could argue is now misleading, because we're not taking into account acid strength, and we might be throwing away a drain oil before we've got to a critical ion content. So perhaps a review is required, but it depends how you define when that oil needs to be replaced. Because if you're using TAN TBN crossover, as Matt's described to you, that's not the best way to do it.
Okay, thank you. Next question is for you, Matt. Is there any specific relation between nitration and drain interval? It has been observed more nitration in gasoline vehicle than the diesel vehicles. Can you throw some light on it?
Yeah, so I would agree with that second point, that nitration is more of a phenomenon for gasoline than diesel. Nitration in and of itself doesn't necessarily negatively affect the lubricant. So the engine doesn't really care if some of your molecules are nitrated. The real issue that you get with nitration is that once the lubricant is nitrated, that will accelerate oxidation. So nitrated groups will thermally decompose to produce more free radicals and more species that will oxidize the oil. And the ultimate negative consequence of oxidation is that you get oxidative degradation and oil thickening. So really, I'd say that's the key concern for high nitration, is that you accelerate that process of oxidation, degradation of the lubricant, and viscosity increase. And it's a viscosity increase that will then impact the operation of the vehicle.
Okay. Next question is again for you, Matt. Does the IPH test method work with different fuel types, for example, HVO, ethanol, high biodiesel content?
That's not something we've really looked at, IPH measurements on pure fuel. So really, the application that the method was designed around and that we've used it for is measuring lubricants. And so I would say I can't give a yes or no answer to that question, I'm afraid.
Can I just add there, Matt? I suppose if you're considering the use of those fuels and how that relates to engine oil degradation, no, I'd say it would definitely be applicable, because we know the use of, for example, biofuels can lead to more organic acid formation in the lubricant as things degrade. So the use of biofuel, IPH should be picking up acid strength and therefore corrosivity. So it would definitely be something that we'd advocate using from that respect.
Yeah. Next question is for you, Dave. Are there any specific concerns around corrosion and acidification linked to electrification?
Oh yeah, good question. So electrification is a very broad topic, as I'm sure the audience are all aware. There's a lot of different architectures, lots of different vehicle architectures, but I suppose to answer the question, I'll focus on plug-in hybrid electric vehicles, or PHEVs. So in these architectures, you have an internal combustion engine and you have your electric motor with battery packs. And you can drive either fully electric or a mixture, or on the combustion engine alone, depending if the charge is depleted or not in those batteries. And as such, the operating conditions of the engine are essentially more extreme than we were typically used to in traditional vehicle architectures. So we can get much lower operating temperatures, and it's also possible to get higher operating temperatures too. If the batteries are depleted, for example, and you're driving relatively fast for a long period of time, the engine might get hotter than traditionally engines used to. So in the lower temperatures, we can get more condensation, we can get more water that ends up in the engine oil. And I told you about how we have to neutralize the acids that get into that water earlier on, but that acidic water can be very corrosive. And then at the other extreme, higher temperatures, we get more oxidation. So typically a 10 degrees rise in temperature will double the rate of the oxidation. So we get more oxidation, more acid formation at one end of that extreme. At the other end of that extreme, we have more water getting into the lubricant. The acid can go into the water and we get a very corrosive environment. So everything we've discussed today is very important for electrified vehicles. And in certain cases, it can be quite extreme in those vehicle architectures.
Yeah. Thank you. And just last question for you. Are there downsides to using small particle sizes?
Okay, yeah, good question. So I've shown you different performances of different over-base detergents today. And I told you small particles have a high surface area to volume ratio, so therefore high neutralization potential. So it's really a balance. For formulators, it's a real balance, because yes, perhaps you could think, okay, let's use loads of small particles and that'll be a really good performing oil. That's true, but the base will also be used up pretty quickly. So often it's a balance of having larger and smaller particles within the same formulation. That's often a good thing to do. And also you need to think of the secondary implications of these additives because they do other jobs too. They don't just neutralize acids. So you really have to balance the formulation out to get the optimum performance out of both the overbase detergents and acid neutralization, but also other things like cleanliness and oxidation, for example.
Yeah, great. Okay, thank you again to Dave and Matt, and thank you to everyone for joining us today and for your questions. This concludes today's Lubrizol360 webinar. Once you close out of this session, you will be presented with a survey, and we invite you to provide your feedback on today's webinar. In addition, a recording and a copy of the presentation will be made available soon. Enjoy the rest of the day. Thank you so much, everyone.